Hi, good day dear audience. I've mentioned before the formula for a droplet of the time necessary for a droplet to evaporate, whatever, water or whatever. And this formula, as I gave it before, was T equals rho dO squares minus D square over 8 lambda into ln the natural logarithm of 1 plus CO minus C infinity over 1 minus CO. Let's make the outer bracket in the form of rectangular, that's all. As I told you before, that's the time needed for the evaporation or to change the diameter from diameter dO. Of course, this could be 1.5 millimeters, of course, from a diameter dO to a diameter d. After evaporation becomes d, dO becomes d. So that's the density, time in seconds, the density in MKS system of unit, kilogram per meter cube, lambda, characterizing the material and the temperature, and depending on the temperature and pressure during the evaporation and air current. See, here is time, not temperature, of course. And its unit is, as I said before, it's mass lambda, that's its unit, mass per length times time. CO, the concentration at border of the droplet, C infinity, the concentration at a very far distance from the droplet. There are some things I want to emphasize that are parameter, that is JO, which is the mass evaporated per unit area per unit time, and consequently JO at the beginning, the rate of mass evaporated per unit area per unit time square the original radius equals J at any stage of the evaporation times the present radius at that stage, squared, of course, because actually this is J times area, but we have J times 4 pi r square, the area, surface area of a sphere, but 4 pi cancelled with 4 pi, so, or we can say J1 R1 at different stages, not necessarily starting with the original state. J1 R1 square equals J2 R2 square. So that's what we need to start our derivation. Of course, I have issued this before, gave it to you before, to calculate the time needed for the diameter change from the original diameter to a new diameter, or to completely vanishes if we put D by 0. That's rho dO square, just dO square, and D equals 0 over the denominator. So that's all we need to start our explanation how this formula was derived. Now, according to Fick's law, we have that Jc minus lambda dc by dr into r square equals the original evaporation rate per unit area per unit time multiplied by equals JO RO square. To find our formula that I have written some moments ago is to rearrange the terms and then integrate. Let us start here. That is now J C r square. One could say how this quantity is already J r square is equal to J O r O square. So how it comes that with that all that expression still we haven't exceeded the value of J O r O square? That's because C has decreased. C at any stage is less than CO, and this quantity dC by dr, C is decreasing. This means that this quantity is negative, so minus a negative quantity, this means we are adding to this the value of JR square, because C decreases, C is its maximum value is unity. As I said before, C is the ratio of the mass per unit volume at the present state, instantaneous over L instantaneous over M maximum, the maximum mass a given volume can hold. So it can never exceed unity. So So here J R O square C R square minus J O R O square, J O R O square. We transfer J O R O square to this side, it becomes the negative side, equals lambda dc by dr of lambda dc by dr transferred to the right hand side with positive sign, and JOR square transferred to the left with negative sign. As I said before, JR square equals JORO square, or JORO square is equal to J1 R1 square times J2 R2 square at any stage of the evaporation when the radius or the diameter is diminishing. So here this is JR square is equal always to JORO square, so we'll take JORO square common factor into C minus 1, JORO square times 1 equals lambda dc by dr times r square. Okay, so we'll now perform cross multiplication. So it will be here JORO square over lambda. The numerator of the right hand side will be transferred to the denominator cross multiplication to the denominator of the left hand side over lambda times dr over r square. Cross multiplication also here, r square became the denominator here and the r in the denominator here, equals to dc over c minus 1. Okay, now we can perform integration. This is constant, JORO square over lambda. Lambda constant for our case at a given temperature, at given air currents, surrounding air currents and pressure, and integrate dc over c minus 1. So now we have JORO square over lambda into, I just want to remind with the simple integration, integral x to the power n equals dx, of course, dx equals integral x to the power n dx. dx equals x to the power n plus 1 over n plus 1. Here dr over r to square, this means integral r to the power minus 2 dr, which means r to the power minus 2 plus 1. Minus 2 stands for n here. Minus 2 plus 1, which is equal to r to the power minus 1 over minus 1, which is equal to minus r to the power minus 1, which is equal to minus 1 over r. R to the power minus 1 is okay. So here we'll get, let's transfer the minus sign here to the whole quantity into 1 over r equals ln c minus 1. Can rub this now and then continue our derivation. So things, ln c minus 1, last one might thinking ln c and then minus 1. No, it is as a whole, ln c minus 1 as a whole, which is clear from the derivation here. It's okay now. I'll leave this for some while, for some reason. I'll explain it. It's about some reason regarding the limits of integration. So here of course, our integration is from the first condition to the final condition, which is from RO to R infinity, and here from CO at the surface of the droplets to the concentration C infinity at a farther distance, and R here is R infinity is R when the particle nearly diminishes. So what we have here is to integrate. So simple. Here we substitute from the upper limit to the lower limit. We'll take minus common factor here, so we'll have 1 over RO. RO becomes minus 1 over R infinity. We have taken the minus common factor. R infinity here minus minus, which is positive as here. Okay, so this quantity as a whole now becomes positive. So that's very nice. Equals ln A minus ln B equals ln A over B. So we'll apply it here. Equals ln C infinity minus 1 over C naught or C0 minus C infinity minus 1 over C0 minus 1. That's it now. So we have here JO RO square over lambda into 1 over RO minus 0. R, this is supposed to be a very large distance approaching infinity, so this is RO, so here we can, so this is JO over lambda equals, now we can multiply the numerator and denominator here by minus, we'll have ln C infinity, then 1 minus C infinity over 1 minus CO. Let's play a game here and subtract from this quantity minus 1 and add plus 1. Okay, nothing changes. Then, okay, let's see what this yields. It will give us ln 1 minus C infinity minus 1 minus CO over 1 minus CO. All this plus 1. Because the minus 1 here it became with the denominator minus 1 minus CO, which is minus 1. Which yields to minus 1 minus 1, that makes nothing. Minus minus CO, so the CO becomes here positive, minus C infinity over 1 minus CO. Plus 1, don't forget the 1. Now let's call this equation 1, that's the first relation that holds between JO and RO and lambda and the concentration. Now let's try another relation, logical principle. Okay, you know that the rate of decrease of mass should be equal to d by dt of rho times 4/3 pi r cube. That's for a sphere, of course. That's considering the droplet as being RO. At the same time, you have that JO is the rate of evaporation at the starting of studying the evaporation per unit surface area per unit time. So this should be equal to this rate, JO times 4 pi RO square, because this is per unit area per unit time. So here we multiplied by the area, the rate of decrease of mass. But this is a decrease, so we'll give it a negative sign because this is a positive quantity. Okay, so now so simple, so easy. Let's differentiate this quantity. To differentiate this quantity, we have that just for remembrance, if you have two functions, z is a function of y and or comma, no problem, or y equals f of x is a function of x, then dz by dx equals dz by dy times dy by dx. Surely you remember that one of the fundamental rules of differentiation. Okay, having remembered this, we'll start differentiating. So this would be d of 4, rho being constant. We'll put it outside the differentiation. Rho times the differential of 4/3 pi r o cube, and then the differential dRo by dt. So we'll have now rho. Let's leave this inside the integration, although it is no problem. Okay, we'll put here 4 pi times d by dr, differentiating of r cube dr. RO cube. This gives us 3 RO square. dx to the power n by dx equals n x to the power n minus 1 over 3, which is here in the denominator, multiplied by d RO by dt. Okay, we haven't equals minus JO times 4 pi RO square. Okay, so here 3 cancelled with 3, 4 pi RO square, here 4 pi RO square cancelled with each other. So we are left with rho d RO by dt equals minus JO. Very nice. That's relation 2. But if you remember, we have got the previous relation, which is lambda over RO into ln CO minus C infinity over 1 minus CO plus 1. That's the relation obtained before. Equals JO. That's relation 1 obtained 2 or 3 minutes ago. Okay, that's very nice. So we'll equate these two. But we'll give this a negative sign. We cannot say that JO equals minus JO. We have here minus rho d RO by dt minus, to make it equal to JO, equals lambda over RO into ln CO minus C infinity over 1 minus CO. Let's write infinity better. Sorry, my handwriting is not all right. Plus 1. Okay, it's okay here. So by cross multiplication, it is minus rho times RO dRO. It is x dx as if it is x dx. Over, let's transfer all from the beginning. Lambda by cross multiplication here, lambda. And the ln term in the numerator becomes in the denominator of the left hand side, ln into ln of CO minus C infinity over 1 minus CO plus 1 equals dt. We have only in the right hand side dt. So here the next step will be integral RO dRO. It's RO square over 2. Integral x dx, x square over 2, RO square over 2. But note here we should have been integrating from RO to the new r, to the smaller r, because we consider that the particle diminishes from DO, whose radius is RO, to the new smaller diameter. Or if we put d by 0, this means the time necessary for the particle to completely vanishes or evaporates. So here we have RO square, from the upper limit to the lower limits. Here r square over 2 minus RO square over 2 times rho, of course. This is over lambda ln CO minus C infinity over 1 minus CO plus 1, all this This is the length term, or this is the length term. CO minus C infinity over 1 minus CO, all this plus 1, okay? Here, we'll take the minus common factor. This is minus rho over, we take minus common factor from these brackets, it becomes RO square over 2 minus R square over 2. So this is minus and minus, so the whole quantity now becomes positive, minus minus, and we have lambda times, let's not write it, I got bored from that, the length term equals T, minus times minus, so it is rho into, note that RO equals dO over 2, and consequently R equals D over 2. So here we'll have dO over 2 all squared, because this is RO squared, over 2 minus d square over 2, d over 2 all square, over 2 over lambda times the length term. We obtain here dO over 2 all square, that's dO square over 4, over 2, that makes dO square over 8. So here we got the final formula. So simple, so easy. Let's write it. It is rho dO square minus d square, and taking the 8 common factor here, dO over O square over 8 minus d square over 8, taking the LCM and then multiplying both by 8, because this is dO by multiplying here by 8 and the denominator by 8, we get lambda into the length term, length CO minus C infinity over 1 minus CO plus 1 times 8. That's 8 lambda. 8 lambda length equals T. So this is our golden formula I have given in my previous video 2 months ago without proof. So we have reached, I think I have explained thoroughly. I hope no one have cursed me for the long derivation. And luckily, I believe anyone who was intending to curse me would have closed the video instead of cursing me. Sorry for the long derivation. Hope you, anyone who interested in math, have enjoyed it. Okay. Goodbye, my dear audience.